All right, everyone, so this is the last video on our Unit 3 topic. So we're going to talk about the periodic trends or the patterns that we see in the periodic table. But in order to do that, we need to talk about why we see these patterns, and it's all due to the attractive forces that hold the atom together. So these attractive forces are the force between, the protons and the electrons. Okay, now remember that protons have a positive charge, but electrons are negative. And so that force between them, they're attracted to each other like magnets, okay? And this force is what holds the atoms together. Now, when you look at the atoms in a row or a period, so remember a period is the same thing as a row, let's compare a couple of elements. So let's look at lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay? As you go across the periodic table, what happens is you are changing the atomic number. 3, 4, 5, 6, 7. Oops, I'm putting them in the spot where their mass goes, though. So let's do that correctly. 3, 4, 5, 6, 7, 8, 9, 10. And so because the atomic number is increasing, that also means you're increasing the number of protons. So as you go from left to right, you increase the number of protons. And what happens is when you increase the number of protons, that makes the attractive force stronger. So the attractive force gets stronger as you go from left to right across the periodic table. And that's because you increase the number of protons. So that's like saying if you are in a classroom and you increase the number of teachers, you're going to increase the force that the students feel from the teacher. So if there are 5 Miss Nichols in the room, then that's 5 times the amount of influence that I would have. Now, when we talk about a group, though, now notice all of these, when we're looking at the period lithium through neon, those are all on row 2. So they all have 2 energy levels, right? So that stays pretty consistent. But when you go down a group, so let's say we're talking about hydrogen, and then we talk about lithium, and then we talk about sodium, and I'm not going to go into too much more. Hydrogen is on row 1, so it has 1 energy level. Lithium's on row 2. It has 2 energy levels. Sodium is on row 3, so it has 3 energy levels. And so if your protons are at the center and your electrons, like the very furthest valence electron, right, is getting larger or further and further away. So as you go down a group, you are increasing the number of energy levels. Now when you do that, the distance between the protons and the electrons gets bigger. And what happens is when you have a greater distance between the protons and the electrons, that means you're weakening the influence. And so when this happens, that means that the attractive forces get weaker. So what that means is if you are in the top right of your periodic table, you're at the top, you're all the way to the right, that's where you're going to have your strongest forces. But in the bottom left of your periodic table, you're going to have the weakest forces. And this is going to be the reason why we see the trends that we do on our periodic table. So let's talk about these trends. The first one we look at is atomic radius. Now, the atomic radius just refers to the size of the atom, Now, when you have the atomic radius trend, what you need to remember is that if you have a strong attractive force, so that would be in the top right corner. And then the bottom left-hand corner is where you have those weak forces that we just talked about, okay? So what happens is if you have a small atomic radius, which I'm going to abbreviate as AR, and I'm actually going to write it below it. If you have a small atomic radius, that means that you have a strong force because the protons are pulling the electrons in tightly. It's kind of like when you pull really tightly on a belt, it makes the size of the atom smaller, or the size of the belt smaller. And so that means if you have a large atomic radius, that means you have a weak force. Okay, you're not pulling on the belt very tightly or at all, and so it allows it to expand. So that means if you have strong forces, you have a small atomic radius, and if you have weak forces, you have a large atomic radius. So the way that looks is if you're looking at the left to right, we know that the attractive forces is getting stronger. So this means that the atomic radius is going to decrease as you go from left to right. And as you go down a period or down a row, we know that the forces are getting weaker. So that means the atomic radius is going to increase. Okay, so this is what's happening there. Okay, so we've got atomic radius, all about strong forces and weak forces. If we're looking at ionization energy is the energy required to remove an electron. Okay, so the energy required to remove specifically a valence electron, not just any electron, but a valence electron. Now, again, remember, top right, you've got strong forces. Bottom left, you have weak forces. So the key thing to think about is, okay, what happens if I have a high ionization energy, which I'm going to abbreviate as IE. Okay, if I have a high ionization energy, that means it requires a lot of energy to remove the valence electron. Okay, if it takes a lot of energy to take something away, that means I'm holding on to it really tightly, and that means that it requires strong forces, those strong attractive forces, because it means that the atom is holding tightly to the electron. Okay, it's holding tightly to the electron, which means the opposite is true, that if I have a low ionization energy, that means that there is a weak attractive force. It's weak forces, it's not holding very tightly, so it's easy to take away the electrons. So this means that as I go from left to right across the periodic table, my ionization energy is increasing because my forces are getting stronger. But as I go from top to bottom or down a group, that means my ionization energy is decreasing. Okay, because the atomic radius is getting bigger, the forces are getting weaker because there are more energy levels, so it doesn't take as much energy to remove it. Let's look at electronegativity. Okay, electronegativity is the ability to take or gain a valence electron. Okay, now if I'm trying to take or gain something, that means I probably want to have strong forces. So again, if our strong forces are in the top right and our weak forces are in the bottom left, that's always the same. Okay, if I have a high electronegativity, which means I'm going to abbreviate that as EN, that means that I have strong forces. I am good at pulling and taking other electrons. Okay, so Let me make sure I did that. Okay. But if I have a low electronegativity, that means that we have weak forces, because if I'm kind of weak, I'm not going to be good at taking electrons. So this tells us that as I go from left to right, the forces are getting stronger, so that means that my electronegativity is also increasing. But as I go down the periodic table, my forces are getting weaker, and so that means that my electronegativity is going to decrease. Notice that electronegativity and ionization energy have the exact same pattern, and that it is the opposite of the atomic radius. Okay, so notice that for your patterns. Now, if we look at reactivity, okay, reactivity in my mind of metals, okay, specifically, is going to be the speed at which the metals lose valence electrons. Okay, because that's their goal in order to react. Remember, the very first video in this review series talked about valence electrons and how metals are going to lose valence electrons to form cations. Okay, so if I'm trying to lose valence electrons, so if the goal, right, so if the goal of a metal is to lose valence electrons, okay, this means that they need to have weak forces. Okay, so remember that the strong forces are in the top right part of our periodic table, and the weak forces are in the bottom left. Now remember, we have a staircase that separates the metals from the nonmetals. So our metals are located on this side of our periodic table. But that means when I'm talking about maybe our alkali metals, right, in column number 1, as I go down the periodic table, my forces are getting weaker, which means it's easier to lose those valence electrons. So that tells me that my reactivity is going to increase, okay? And that also means as I go from left to right, okay, my force is increasing, which means it's harder to lose the valence electrons. So it means it's less reactive, or that the reactivity is going to decrease as I go across. So as we're comparing, for example, let's say sodium versus calcium's not beside it, magnesium. Okay, sodium versus magnesium. We would say that sodium is more reactive than calcium. And we can also explain that because of the valence electrons, right? Because sodium has 1 valence electron, but magnesium has 2. So sodium only has to lose 1 valence electron, right? It has to lose 1 valence electron, but calcium has to lose 2 valence electrons, so it's going to take a longer amount of time. But if we're comparing something like sodium to potassium, which is underneath it, we know that potassium has weaker forces because of the number of energy levels, so we could say potassium is more reactive than sodium. Okay, and so we can use that comparison. Now, the very last thing is we want to talk about reactivity again, but for nonmetals. So remember, nonmetals are going to lose, or excuse me, they're not going to lose. This is going to be the speed at which nonmetals gain valence electrons. Okay, so they're trying to gain valence electrons. Now, if I'm trying to gain valence electrons, okay, so if I'm thinking about my goal of nonmetals, okay, the goal of nonmetals is to gain valence electrons. That means I'm going to want to have a strong force because it will be easier to take or gain valence electrons if it's strong. Now remember, that staircase means that when we're talking about nonmetals, we're literally just talking about this small portion on the right side. And we know that our strong forces are at the top of the periodic table, top right, and our weaker forces are at the bottom left. And so that means when I go from left to right across our nonmetals, my forces are getting stronger, so that means my reactivity increases as we go from left to right. But as I go down the periodic table, okay, my forces are getting weaker, and so that means that the reactivity decreases. Okay, so when we're looking at nonmetals, this is what we have going on. So for example, if we're comparing oxygen to fluorine, we would say that fluorine is more reactive than oxygen. Okay, and it's because it has stronger attractive forces. We also know that fluorine has 7 valence electrons, so it only needs to gain 1 valence electrons, whereas oxygen has 6 valence electrons, so it needs to gain 2 valence electrons. So it's just going to take more time, okay? But when we're comparing within a column, so maybe fluorine versus chlorine, okay, we would say that fluorine is still more reactive than chlorine, and it's because of those stronger attractive forces. So for this video, you should now be able to compare the reactivity, the electronegativity, the ionization energy, and the atomic radius, and the forces, the attractive forces, between any set of atoms on your periodic table.